to my presentation. My name is Tim Bittner. I'm from Karlsruhe Institute of Technology, and my talk today will be about Qubrabench. Qubrabench is a framework for hardware-agnostic quantum algorithm benchmarking. First of all, the benchmarking question. The question that most of us or most industry people have is, what would quantum actually do for me? Like, I'm fine with theoretically proven quantum advantage, but in the end, like, can I just buy a quantum computer and make things go faster, cheaper, better? And to illustrate that, I've brought a little example, something everyone always does, which is like search an element in an unordered list. In this case, this is Python code, and we have the list of elements 1, 2, 3, 4, and 5, and we search for the element which value is 3. And I think everyone who's ever touched program code can agree that usually you would go about and write a simple for loop and search each element iteratively and find out if your value is matching what you want to find. This is fine, but there's also another way, which is a little bit more mathematically, to also solve this problem, which is formulated as a query for a general search function over the element set and formulate a predicate which returns the value true once your target value has been found and matched. And if we write it on this way, we can derive something like this, where we can say, hey, okay, once our list grows bigger, we can see the runtime increases exponentially for classical problem instances, but for quantum, we might have a better growth factor. And to get this kind of transformation on the right, like this reformulation and then the plots in comparison, I brought Qubrabench today. So taking a step back, what do we actually need for benchmarking? We need 4 things. We need problems, we need problem instances, we need algorithms, and we need a runtime framework. Where do these things come from? The problems come, for example, from project proposals, like we have in Sequoia or other quantum projects. Problem instances are usually derived from industry partners, like real-world instances. They have problems that need to be solved, although they might be toned down a bit for the current state of quantum computing. And then there are algorithms, which usually come from researchers working their butt off to find new ways to solve these problems with the new resources that quantum provides us. And then at last, which is usually missing, we actually need a runtime framework. So something that puts all these things together and combines it and makes us able to derive meaningful statements. So then how do traditional benchmarks work? Traditionally, you need to decide on a single variable that you want to benchmark. You have this whole complex system which consists of machines, like you can vary the kind of computer that you run your program on. You can also change out algorithms, like do you want to solve your problem with this or with that algorithm? And also the problem instances change, of course, because it matters if you have a delivery problem with 24 cities or 24,000. What you need to do with it is decide on one variable and then fixate all the others. So in this case, we want to do stuff with quantum computing, and we want to choose a set of problem instances that is known so that we compare algorithms. So which algorithm is better suited for quantum. Once we have that, we measure our vector of interest. That means we execute actually an algorithm for the problem instance on a concrete machine, or for many algorithms, and then we compare stuff. For example, CPU seconds or memory footprints. And using these comparisons, we can then tell, hey, this algorithm performs better, or the other one is better, or both are kind of, I don't know. So then, this is classical benchmarking. Why doesn't this work for quantum yet? Quantum computers are small and noisy. We call that NISQ, noisy intermediate scale quantum computing. So that means they can only handle small circuits, that means small algorithms, and small problem instances. Small instances, on the other hand, are trivial to solve for modern classical machines, so honestly, what's the point of even bothering with quantum benchmarking then? And even worse is that actual quantum advantage is theoretically projected to only occur at larger instance sizes. So not only can we not run these larger instance sizes because of the NISQ thingy, we also don't expect advantage on the small instances. And to prove this point, I've brought a little industry use case. What you can see here is a feature model which is used to model variability of a car. Imagine all the ways you can configure your Mercedes when you go over to Mercedes-Benz and order your new vehicle. So this is a way to formalize that and say, hey, we can have different kinds of engines. For example, here we have an electric or a gas engine. Of course, they are hybrids, so we could have both of these features. But just take away that this models all possible ways we can configure one specific car. And finding a valid configuration for this kind of feature model already requires 28 qubits. And I don't know how much you're into quantum at all, if you're new to it or not, but 28 qubits is already larger than the quantum computer we have in Germany. So that's already a problem, and this car doesn't look like it has that many features. And furthermore, the gate depth is also over 500 gates, so this quantum computer wouldn't work at all. Which means comparing quantum simulators and quantum machines in general is infeasible. It's technically possible, but it's kind of very theoretical, and in the end, simulation overhead and limited size make obtaining relevant results nearly impossible in terms of comparing runtime and memory footprint directly, how you would do with classical machines. And if we go back to the question of what does quantum do for me, this ignores stuff like queue times and wait times to just actually perform your calculations. So what's the point if your calculations is only 5 seconds, but you have to wait 24 hours to actually do your calculation in the first place? So now, what actually can we do? What is the answer? So let me provide you with the state of the art. That's stuff that's already there, that's established. We have different kinds of pillars. One of them is theoretical co-execution, which is fancy words for saying, actually, let's just execute our problem classically, because we can do that, and we can do large instance sizes. They might be slow, and they might be slower than what we expect from actual quantum computing results, but hey, we can execute them, and it kind of doesn't matter. Because if we annotate our classical solutions with points in the code and say, hey, this thingy could actually be a quantum subroutine, for example, a quantum search, then we can derive subroutine costs. And with these subroutine costs, we can say, hey, okay, classically, this takes us 100 seconds. But if we were to do it on a quantum computer that's sufficiently powerful and sufficiently error-free, then we would only have 45 seconds for this quantum search routine. And this allows us to use the problem instance sizes that are realistic. And all these things are established. They are there. People have thought about how to replace subroutines with quantum subroutines. People have thought about executing the classical program and then deriving quantum runtime from that. But what was missing was something that envelops it all and that actually provides means of connecting the pillars and doing just that all at once. Let me drive home an example. It's going to get a little bit more messy now, but bear with me, it's going to be fine. We have Q-search, which searches for an element in an element list, whatever that may be. And we have a use case that's called weighted max k-set. maybe first, what actually is weighted max k set? Just imagine you have a set of clauses, and each of them is a disjunction with k Boolean literals, and a set of weights, which is one for each clause. Then try to maximize the weight of the satisfied clauses, which is mathematically in this formula, but it's just the same, maximize the weight of the satisfied clauses, over all assignments of the Q variables. Which just means find me a good, satisfying solution for my problem that's the best in some way. Turns out this is computationally NP hard for k larger than 2. And there exists a heuristic to solve this, so it's actually just an approximation, but it kind of is good enough, which is called hill climbing. And hill climbing works by starting out with a random assignment. Just take any solution, I don't really care. And then look at how good is this solution, and then modify the solution in a single place, for example, flip one literal, and then take a look at, hey, how is this modified solution going to work out for me, given my maximizing parameters. And then we just do this over and over again until we cannot change our solution in any way that retrieves a more meaningful result. In depth, this could look something like this on the right-hand side, which is just that hill climber example implemented in Python. And then I've marked with these arrows the instrumental Qubrabench API calls, which are search and max, depending on if you want to take any neighbor that's better or like the best neighbor. But this detail kind of doesn't really matter. It's just choose one, and then the slopes of the resulting benchmarking graphs will be slightly different. The break-even point will be slightly different. But essentially, that's just what was on the last slide. Programmers might be familiar with this. These are the API docs for QSearch and Qmax that I've presented in the code just now. You can see we provide with Qubrabench API as part of the API sophisticated documentation where you can read up what the parameters are, how the function signature is called, and how to actually use it in your code base. Then for QSearch itself, QSearch works kind of like this. We have a classical stage that's just used to only invoke quantum cost once the search space is sufficiently large, because if our search space is super small, then we can just classically perform better than quantum. But if we get to the quantum stage, we actually manage to have this algorithm that runs Grover search. I don't know if you're familiar with Grover search, but it looks kind of like this. We have some kind of initialization where an equal superposition is created. Then we have a phase oracle that encodes our problem instance and repeats these search over and over again until we actually can measure results. And once we measure results, we actually have performed a quantum search. Why should you care? Actually, you shouldn't, but you want to know how fast it is and how much time it takes. And for that, you need to analyze the query cost, like how often is this quantum subroutine executed for your given problem instance. And as it turns out, if at least one solution exists, it's something like this, and also like this. Do you want to do this yourself? No, you don't. It's really hard to come up with these formulas and costs. And furthermore, there's another case where no solution exists, which also adds a classical offset. And what I'm trying to make as a point here is, this is too complicated just to find out if quantum does anything for you. You don't want to study math and physics for years on end just to see if one algorithm will work out for you. It's just not reasonable. Luckily, this holds true for the QSearch subroutine given any particular size. In fact, for the analysis, we don't need to do new calculations. We just need to change the inputs. And turns out we only need n, t, epsilon, and k. What are these things? N, we know because we choose the problem size. We know how many elements are in our list. We know how many cars we can build. Epsilon, we need to define for an acceptable quantum error rate. It's safe to assume that no near-term or mid-term or maybe even long-term quantum computers will be perfect. So let's just say, hey, we are fine if it fails 1 in 10,000 calculations, or if 1 in 10,000 results is slightly off. It's fine, we can just run it again. But T is entirely runtime dependent. And that's an issue, because that means we can't do the entire analysis beforehand and statically, but we actually need to execute code, which is a problem because we can't execute quantum stuff, as I said in the beginning. So this is where the co-execution then comes in. And just for the sake of completeness, it has been empirically determined that k equals 130 is sufficiently small as a sampling size that yields good results. That's the kind of point where scientists still need to tweak on the things, which is just like, yeah, we kind of don't really know why 130 provides good results, but 130 does provide good results. So then coming back to the benchmarking hill climber, what we want to do is we initialize a real problem instance. We initialize a real input vector that solves our problem. And then we evaluate the current vector and search the vector neighborhood for improvements by tweaking aspects of our solution. And then we can actually do the benchmarking, because in each step we can determine the quantum costs and calculate the formula inputs that we need to evaluate the query cost formulas. And in this step, we can actually just take the runtime dependent parameters out of our calculation because they have been calculated, because we are running the stuff classically. And we need to do this over and over again. So that's another point where we can just do it beforehand, because we actually have to calculate T a bunch of times. Like for one problem instance, we need to calculate these runtime dependent parameters for thousands of times. So manual effort is insane and basically not worth it. Then afterwards, we can compare the output of quantum and classical plots, and this is the point where all of you have been waiting for, the answer to when will quantum do stuff for me. And if we were going with this hill climber example, we can see here a few different plots for solving max k-set. We have different parameters you can see here for k2, r3, somewhere along these lines. There's a crossing point. It's just different plots to drive home the point that there are different input parameters, but all lines still converge. You can see these are running together. The x line is the quantum cost, by the way, and the point line is the classical cost. So what we ideally want to see as quantum researchers is that the x line is below the dot line, which means, hey, we actually have quantum advantage for our problem use case, or we measured quantum advantage. And yeah, all of these graphs seem to converge to that point. So given sufficiently high inputs on the x-axis, actually quantum seems to provide a speed up. And furthermore, besides the fact that we actually have quantum advantage now, this is machine and runtime independent. So it doesn't matter how much time we actually spend evaluating this, we now know that this algorithm is proven to be better for this problem set. If you want to read more, if you're a developer and want to look more into this max k-set and are interested in more, then I can just cram into a few PowerPoint slides on the stage. Feel free to take a look at our GitHub. We have a notebook provided which goes all over the mathematical side and background of max k-set, and then also quantum solutions using Grover search, quantum search. And the QR code for that is here. And with that, let's look at the different benchmarking levels for Qubrabench. We have different user groups in mind. For one, on the left side, we have the Qubra subroutine API. This is usually something done by quantum algorithm designers and theoretical analysis. Software engineers might implement these routines and cost collections into the framework, but then the next higher up user can take example use cases, for example, stuff like the hill climber, define their problem instances, implement their classical solution. In most cases, they might already have an implementation for their classical solutions, and then just replace the classical routines with Qubrabench APIs, which all of them conglomerate in this last group, which is everyone. Everyone can just check out the GitHub repository, run and plot their own examples, and continue finding out if Quantum does something for them. The examples currently present in our GitHub are not only hill climber, we also provide shielding, SAT solutions, and community detection using Louvain algorithms. All of these are present today and implemented. And with that, I would like to invite you all to contribute to Qubrabench today. It's open source and free on GitHub, on the MIT licenses. Check it out and take a look at it. Maybe if you don't want to contribute code, feel free to write an issue with, hey, this is my industry problem. Can you take a look at this? Like, can you benchmark this? What about this? So just feel free to add issues if you don't want to code yourself. Yeah, that's the end of my presentation. Thanks for your attention.